Now with electricity, it's one of the concepts or topics that now starts from grade 8, grade 9, and grade 10. So it further goes into 11 and 12. So everything that I'm going to try and do is basically to try and summarize and comprehend everything from grade 8 to grade 11, and maybe further extend few elements that will now you are going to need as we look into grade 12. But what is key here is everything that we are going to focus on. We'll focus now on the resistors that we have. So one can have now resistors in series, and one can have resistors now in parallel. Because now everything that we are going to be focusing on will now be in a point where we look at resistors and how they influence each and every single circuit we have. So having resistors in parallel, we are just going to try and explain exactly what is now the difference between the two. Once we establish the difference, it makes it easy for us now to be in a position of exactly understanding how a circuit operates, which path does the current take. Because once I am aware of the path taken by the current, everything now is going to become nice and easy. So let's have a diagram of resistors connected in series. So it will be resistor 1 connected now to resistor 2, and let's have now resistors connected in parallel. It will be resistor 1, and now resistor 2, and in that connection also. But what can one say here? One can easily say, if I have my current here, which is now this red line, I can easily see that the current now passing at R1 is actually the same current passing at R2. So it says to me, one can easily say I total, which is now I for the current, is actually I total equals to I1, which is equals to now I2. So it basically says, regardless of any point that I choose, in the resistors connection, if they are in series, it basically says the path taken by the current should be the same. So the current at R1 and the current at R2 should be the same. So this is one of the key elements that one needs to be focusing on. But what about resistors now in series? If my current is coming here, which is now the red line, is going to split into two, such that we can have current now passing in R2 and now current passing in R1. So it basically says, for me to fully understand how the current will work or will flow in a circuit in which we have resistors connected in parallel, it will be now I total is equals to I1 plus now I2. But we further move on to say, what if now I focus on the potential difference? So the potential difference when I have resistors in series, V total, is just V1 plus now V2. But when I have resistors in parallel, it's Vt is equals to V1 is equals to V2. What is this statement actually saying to me? It's basically saying if I have resistors now connected in series, they divide the potential difference into two. So if I am going to connect a resistor here, a voltmeter on this one here, which will be V1, and connect another point there, which is now V2. It basically says to me, if R1 and R2 are not identical, maybe we should say R1 it's not equals to R2, so they are not identical. So if they are not identical in this sense, it basically says to me, they are going to have different voltages. And once they have different voltages, I am going now to add the two voltages for me to get the total voltage. But once I have established that I have resistors that are connected in parallel, then I'm going to have the same voltage across each each resistor. So if I do connect a voltage here on R1 and connect another voltage here on R2, it basically says now V1 and V2 and the V total. The question is now, what is the V total? V total is actually the total voltage of the circuit. So now in grade 11, the focus is only now on the external voltage. Once we introduce the concept of grade 12, then we look into the internal voltage, or most people call it lost volts. That is now when we introduce the concepts of internal resistance. Now, one must ask, why necessarily focus on current voltage for us to understand this? Because the key rule is we are intending to go and apply a specific rule. So once we apply that specific rule, it will assist us to know exactly how to apply these concepts that we are trying to explain here. Let's move on and say now, what will happen to the total resistance? So R total or RS will be R1 plus now R2. And 1 over Rp will be equals to 1 over R1 plus 1 over R2. Now here comes the catch, and here comes the tricky part. What is the tricky part? The tricky part is always when I connect now my resistors in series, I am going to have higher resistance. So adding, maybe I should write it down also, adding more resistors in series increases the total resistance of the circuit. That is now very, very important. So we need also to highlight to say, by adding more of the resistors in series, we are actually increasing the total current or the total resistance of the circuit. That is now very, very, very important. But furthermore, if we add now if we adding resistors or more resistors, adding more resistors, in parallel decreases the total resistance of the circuit. So this is now the difference between the two. So once I have resistors in parallel and I want to add more of the resistors, I am actually going to decrease the resistance. So actually, if I want to decrease the resistance of the circuit, what must I do? I must just connect my resistors now in parallel. So once I connect them in parallel, it is going to allow me to have now what? A smaller resistance. And one should ask, what is resistance actually? Resistance is just now the ability of a conductor to restrict the flow of charges. So if I have now a higher resistance, it means now the current within the conductor will struggle now to flow. So if I have a lower resistance, then my current will flow now easily in that metal. So with this being said, I usually try to say this is few concepts that if we fully understand how one can apply all this, the electric circuits becomes easy, because when we look into the hints that I'm going to share later on, it's for you to be in a position to exactly know which connection are you facing or are you working with. If now it is now a series circuit, there is now an approach of how to go about it. If there is now a parallel circuit, this is now a way to go about it. But remember, in an exam, you will be exposed now to the combination of the two. So once we have the combination of the two, there will be now hints as to how to go about that. So I'm going to give you now some timer, something like 50 seconds for you to digest this. And if there are any questions, you can feel free to ask. Now that we don't have any questions, we use an analogy called SAPD. And we also have another one, which is paid. But what does this say now? It says to me now, when I have a series connection, resistors are now potential dividers. Potential dividers. Now, when I have a series connection, so this is now for a series connection. So once I have a series connection, the resistors are called potential dividers. But when I have now a parallel connection, it means this for I is for current. So they are now current dividers. So what is important is, once I have established that the other ones are current dividers, means now my current is taking two paths, then I definitely know that the resistors are connected now in parallel. So these are some of the analogies that one use in order to remember all this nice science that we need now to be looking into. But now, if all this concepts are being done in such a way, is there a law that one can apply when we want to answer questions, when we also want to fully understand how everything will work? Yes, there is. We now come to number 2. And at number 2, we now talk of Ohm's law. Can somebody quickly, maybe the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. Now, in terms of symbols, we say now R is equals to V over I, where V is the potential difference and I is the current, R is the resistance thereof. So let's further explain what is each one representing here. R is for resistance, and then I is for current, and V now is for voltage or potential difference, and this is measured in V, this is measured in amperes, and now this is measured in ohms. So us having Ohm's law, it is a law that we are going to apply in most cases for us to actually perform calculations, for us to be now trying to ensure that each and every concept that we are being faced with or assessed, we are able to answer. But now let's check exactly what this Ohm's law says. It says now the potential difference across a conductor is directly proportional to the current in the conductor at now constant temperature. Remember, it's 2 marks or nothing, so it is always important to state all the key important words, because if one is omitted, then remember no marks will be awarded, and then we'll start now losing a lot of marks. But obviously we have conductors that obey and conductors that do not obey Ohm's law. So what we realize is different conductors behave now differently. So we have one ohmic resistors or conductors, and then we have non-ohmic resistors or conductors. Now, what this basically says to is you have now ohmic conductors as conductors that obeys Ohm's law. Conductors that obeys Ohm's law. What does this mean? It means now the ratio of the potential difference to the current remains constant. So the resistance of the conductor remains constant. So let's just emphasize that. Resistance of the conductor of the conductor remains constant. Very, very important. So the resistance now does not change. Now let's look at non-ohmic conductor. A conductor that does not obey Ohm's law. And what does this mean? It basically says the resistance of the conductor increases as the current increases. So resistance of the conductor increases or does not remain constant. Let's just say does not remain the same. Very, very important things to note down. So because we have an equation which is R is equals to V over I, one can be now in a position of trying to have a graph that will explain more of ohmic and non-ohmic conductors. So this will now differ in terms of as the current increases, then you have your resistance also now changing. Let's have a situation where we are going to draw a graph. But the graph that I am going to draw will be a graph of, let's have our graph. A graph, nice. Then the first graph that I am going to draw will be this one of V over I. And because they are directly proportional, they are just going to give us now a straight line. But what about now if I draw V over I for non-ohmic conductor? It's going to give me something like this. And then we can move it down a little bit. So we are now in a position of explaining what is going to happen. Now let's check. What if I am looking at the gradient now of this graph? The gradient is equals to V over I. But when I check from Ohm's law, the gradient now becomes what? Becomes R, which is the resistance. So it basically says it now stays constant throughout. And when it stays throughout, it basically says it is now obeying the Ohm's law. But let's check what happens now with when I have a non-ohmic conductor. If I have a non-ohmic conductor, I'm still going to draw the same graph for V and I, but obviously I can see that at these 2 points, or across all the points, my gradient is not the same. So I can easily say I will still have the gradient, which will be now V over I, but now this is not constant, as it is changing with now increase in current. Hence now our second bullet says resistance of the conductor does not remain the same. As we increase the current, it's already now starting also to deviate at high current. So as the current increases, also the resistance of the conductor will increase. So this is now an easier way or a basic way of also trying to differentiate between non-ohmic and also ohmic. But now remember, we can also be in a position of being assessed in terms of the graphs. So if you are assessed in terms of the graph, just check what is your independent and what is now your dependent. So in most cases, you'll have different graphs, and from the different graphs now, you will be in a position of exactly knowing. But the key thing is, if once you realize the graph is not a straight line, then it basically says you are working with a non-ohmic resistor. But once you realize that now you are having a straight line, definitely you are working with an ohmic resistor. So what does that mean? It means you are working with conductors or resistors that obeys Ohm's law. And if they obey Ohm's law, then we can use the equation R is equals to V over I. So with that, now I'm going to give you some time for you to digest this. That will be your 50 seconds, so that you can be in a position of digesting everything. If we don't have any questions, then thank you very much. And I believe now we can go into the next section of this topic or chapter, which is electricity. So let me now have a third new page. So from this new page, I'm going to introduce another concept also. And this concept is the concept of power. So we are at number 4. And our focus now is power. First things first, that we need to know is the definition of power. So what is the definition of power? Is rate at which work is done. So rate, we associate it now with time, and work done, we associate it now with energy. So this now says to us, we are basically looking into how much work is done by an electrical appliance over a certain period of time. So the very same power, the SI unit for power is watts, and we only use a capital letter W. Can one represent the given statement in terms of an equation? Yes, one can say P is equals to W over now changing T. So this becomes an equation. This becomes an equation that one can use for calculating power. But now this is not the only equation that we have. I'm going to give now extra 3 equations, and I'm going to assign each and every one of them as to when and how can one use a specific equation. Because if we don't know which equation to apply where, then it means we are in a position of exactly losing the plot. So I'm going to add extra 2 equations, which will now be, the first one will be P is equals to VI. I'm also going to add P is equals to I squared R. I am also going to add P is equals to V squared over R. So all this also very, very important equations for us to take care of and to actually note. Because these equations are equations that we are going to be expected to apply. We are going to apply. And because of that, we need to be certain in terms of which equation are we applying or are we choosing for which specific reason. So as long as we don't know which equation will be applicable to us, it basically says everything that we are going to do will now become a mess. So all these three equations are important, including the one in the blue box. But I am going to explain and try to highlight which ones to use, especially when you have a specific way of looking into the arrangement or the connection of the resistors. So once you have your resistors connected now in series, let's have our line also. And we say we have now resistors in series and resistors now in parallel. So remember what we said earlier on. We said I total is equals to I1, which is also equals to I2. We also said now for parallel, I total is equals to I1 plus I2. And we said V total is V1 plus V2. And we said now V total is V1 equals to V2. We said now RS is R1 plus now R2. Whereas we said 1 over P is equals to 1 over R1 plus 1 over R2. This is what we explained. So let me duplicate this slide because I'm going to need more space for that. So I'm going to use the slide and delete everything here, put it there, and take everything here, move it up a little bit. Then we have created space for us. But if this is the case, when I have my resistors in parallel or even in series, then one can easily be in a point of saying, okay, I have this information. How does it assist me in terms of understanding the concept of power? How does I know which equation will be applicable in this instance? The first thing to understand is, if this is the case, and allow me to draw a circuit quickly with R1 and R2. Or let's have bulbs for us to explain in terms of brightness. So I will have bulb 1 with a wire inside, so will still be R1. I will have another bulb, which is now R2. So with this, it says to me, the current will be the same as we explained earlier on. The voltage will be different and R total will be R1 plus R2. But there is one thing that is common here. One thing that is the same here is current. So for me to compare two resistors in terms of brightness, I need one variable to be the same. So one can say current is the same for both R1 and R2. So the only thing that is changing, remember we said R1 is not equals to R2. This is what we highlighted. It's not equals to R2. But I know the current is the same for both R1 and R2. So it basically says I need now an equation that is going to assist me to ensure that the current is the same. The only thing that is changing now is the resistance. Let's look at the equations we have. P is equals to VI will work because we now have the current and potential difference. But we are interested in this one of P is equals to I squared R. Why that one? Because I am now going to be in a position of changing this to become R1, and I can now change it again and make it now to be R2. So it's just an issue of which resistor I am looking at, which resistors I am comparing. But the fact that I have P is equals to I squared R, then it basically says because of the current is the same, then that is the equation that I should be able to be using. Because if I am going to try and use P is equals to R V squared over R, it is not going to work because I will going to have two now variables changing. Remember, V is not the same, R is also not the same. So that will be now be an unfair comparison. So hence this equation will fall out when working with P resistors in parallel. Sorry, resistors in series. So it's key to understand that for a fair comparison, only one variable should be changed. So we cannot have two variables that are changing. So maybe one should also highlight it for us to be able to remember to say P is equals to V squared over R will not be a fair comparison. A fair comparison as both V and R changes. So hence now we cannot use that equation. So it allows me to say, but now I am only left with two equations that one can use. What are those equations? The equations that are now left will be P is equals to VI, P is equals to VI, and P is equals to I squared R. So this will be now the two important equations that one must use. But how does that tell me in terms of the brightness of the brightness of these specific bulbs? Let's just say, according to P is equals to I squared R, the greater the resistance, the greater the power. The greater the power, but now for the same current. So we must just ensure that the current passing at these two resistors or bulbs that we are comparing are now in series. Hence, we need to emphasize that the current thereof must be the same. Hence, one of the key hints is follow the current path. By following the current path, it will give us now exactly which connection type do we have. Once we identify that the two bulbs that we are comparing are now having the same current, then it's a confirmation to us that they are in series. And if they are in series, I will now be in a position of explaining using now this equation here, because usually this becomes around 4 or 5 marks as to explain why the brightness of different bulbs differs. So we are going to use this as a principle for us to know exactly what is it that we need to use when answering such type of questions. Then they further move on and say now, but we also have P is equals to VI. So P is equals to VI according to that. Now for greater resistance, V also increases. So for the fact that I is the same and V is increasing with V, because now V and R are directly proportional to one another, it basically says now we are going to have an increased power. So now we need also to explain this in terms of these two equations. Usually they will ask us, using the principles of physics, explain why the brightness of bulb A is brighter than or differs from the brightness of B. So this is what we need to be using as now moving forward to explain. So what is key is how we got into explaining why these two equations are the ones that we need to use for us having resistors in series or the bulbs in series. So once we have identified that, believe you me, everything will be easy and everything will be explained here, such that we understand that the current is the same for both R1 and R2, but now P is equals to V squared over R will not be a fair comparison. Will not be a fair comparison, as now what? Both V and R changes. So the fact that the two are changing, then we exactly don't know which factor is or which variable is influencing the brightness. So for us to compare, only one variable must be changed. And in this instance, that variable that is changed must be resistance. Hence now, according to P is equals to I squared R. So I'm going to give you now another 50 seconds for you to digest this, such that we can move now to parallel connection. If you have questions, now this is the right time to do so. Thank you very much. If there are no questions, then we can easily proceed. So now what about resistors now in parallel? Let's connect bulbs in parallel. So we are going to have this one as R1 and this one now as R2. So with this, we explained that I total is equals to I1 plus I2. V total is equals to V1 is also equals to V2. And then we have our resistance now decreasing. Now, current is not the same for both R1 and R2. Current is not the same. It's not the same for both R1 and R2. But there is something that is now the same throughout. What is that? That is our potential difference. So our potential difference is the same for V total, V1 and V2. So it basically says our constant variable here will be now potential difference. So potential difference is the same for both V1 and for both R1 and R2. So if that is the case, it basically says we need an equation where R changes but V stays the same. Because once we have the one where current also changes, it basically says that will not be a fair comparison. So the equation P is equals to I squared R will not work because the I will be changing and also the R will be changing. So the only applicable equations here should be P is equals to VI and P is equals to V squared over R. Why these equations? These equations because one can easily see that now P is equals to VI. The potential difference will be the same for R1 and R2. The only thing that is changing now is the current, because we agreed that R1 is not equals to R2. But let's look at P is equals to V squared over R. What does this say now? It says V is the same for V1 and V2, but R is now what is changing. So with this being said, it basically says one can easily now start saying according to this equation, and this is how you need to start answering this type of questions when you explain the difference in brightness of these bulbs. So according to P is equals to V squared R, the smaller the resistance, the smaller the resistance, the greater the power, the greater the power, the greater the power for the same voltage, for the same voltage. Now, we agreed that the voltage will be the same throughout. So we further extend it to say the smaller the resistance, the smaller the resistance, the greater the current. The greater the current. And according to P is equals to VI, obviously now we'll have now what? The greater power. So the greater power basically means more brightness. So now let's explain this in simple terms. Let's first highlight key things according to this equation. It's important. The smaller the resistance, the greater the power for the same voltage. So now for the smaller resistance, the greater the power or the greater the current according to these equations. So if my resistance is small, my current is more, but I still have now for the same voltage because the voltage is not changing, then I will have the greater power. What does this basically say? It says now when I have my resistors in parallel, the one with the smallest resistance will be the brightest one. But now if I have resistors in series, the one with a greater resistance will have now a greater power. So this now changes as we look into the type of connection that one have. So if the type of connection you have is a series connection, then it is important for us to fully and be aware of how to answer this type of questions. So I'm going to give you some time also, something like 30 seconds for you to digest this such that we can know that everybody fully understands what is now happening here. So let me give you the 30 seconds quickly such that we can move to another concept. Thank you very much. If there's no questions, then we can move to another concept. Let's move to this concept here. And this concept is the concept of cost of electricity. So we will be expected to calculate the cost of electricity. So that is now at 5. Cost of electricity. Cost of electricity. So this is very easy because when we work with cost of electricity, we are actually interested in how much rents or how much money do you need maybe to have a specific number of units. So the formula is cost is equals to amount of kilowatt hour multiply now by tariff which is in this instance the price. So this will be our equation that we are going to use, but it basically says it's power multiplied now by hours, and we multiply that by the tariff. So this one will not be a complicated thing to understand. This will be now our power and the H will be now our time, and the tariff will just be price, and the price must be now in rands. The time must be in hours. The time must be in hour, and then our power must be now in kilowatt. So with that, we will be now in a position to also answer such questions. Let's further move on. The other one is this one, which is at 6. It is called now EMF. So the concept of EMF, it's just now us saying EMF is the maximum energy. Maximum energy provided by a battery per coulomb. It's as simple as that. Now this is the EMF, which is just the maximum energy provided by a battery per coulomb. So what is EMF? Basically, the SI unit is volts or voltage, which is now volts. Let's write it the right way. It should be volts, and just now capital letter V. So with this, it brings now a new dimension of what is it that we can easily say. It brings an element of the battery now, which is the maximum energy provided by the battery. So within the battery, this is what is happening. We have the formula, which is E is equals to I into R plus the small r. So this is just I R plus now I small r. But what is this? This is V external, and this is now V internal, and this is the EMF equation. And mostly you find this one given in the formula sheet. But because this is happening inside the battery, it is introducing us to a different element of what? A different element of internal resistance. Hence, we have now the small r. What is this internal resistance? Internal resistance, let's have a line here. It brings us now to the element of internal resistance. Now at 7, we have internal resistance. So what is this internal resistance? Internal resistance is the resistance within the battery that causes a drop in the potential difference of the battery when the current passes through it. Battery when the current passes in the circuit. So this is now what internal resistance is. So internal resistance, we just basically treat it the same way as we treat our resistors. But the key thing that we need now to note is just that it's an internal, is the resistance that is now within the battery. So if I am told that the battery has a certain amount of resistance inside it, it means somehow will be expected to use this equation, E is equals to I into R plus R, for me to include the concept of internal resistance. But if I am told that ignore internal resistance, then there is no need for me to come and expose myself to the equation of the EMF. So we need now to look for keywords. Keywords here is internal resistance is present, or the battery has an internal resistance. Then we can use this equation to accommodate the fact that the battery has an internal resistance. But if we are told that we can ignore the internal resistance, it basically says there is no need for us to work with the EMF that is given. It will basically be everything up to these slides that we did. So this is now a nice summary of everything that is electric circuits based, that I feel and believe if one has all this as the basic concept, as the basic understanding, then the exam type of questions will be easy for one to do. So from me to you, if there isn't any questions, then I'm in a position of saying I'm giving you a certain time for you to ask your questions. And then if not, then remember, you'll still get the PDF notes of this.